All right, let's finish this thing up. Okay, so off we go to question number 11, which is asking me to rewrite the problem as a single log base. And of course, I had to at least do that one time where I forced you to put some things together. I didn't want the review to be overly long, so please understand there's going to be some things that are on the test that are not on this review because we just did them like minutes ago. I'm not doing a lot of review of certain exponential rules since we just finished them. But we definitely need to change the bases to work. And of course, since almost everything here is base 4, most people would rightfully so assume it would be smart to keep things as base 4. So the change of base formula says we put the original question on top and the original base in the bottom, and we take the log of the base we want in there. Now, as it turns out, this problem isn't too bad because log base 4 of 16 is 2. So this whole thing is 2, which means this 2 and this 2 kind of combine forces, and it's 1/4 the log base 4 of k. So now we're at least in the correct log base. And interestingly, I don't think people always realize that, but these two pieces right here are technically like terms. I've got something minus 2 of the same thing. So of course, we could simplify this to -1 of those things and not bother to put them together as a logarithm before we simplify. We can simplify early and we can simplify as often as we need to. So that leaves me with a log base 4. The x is going to go on top because it's positive. This y is going to go in the bottom. And of course, k is also going to go in the bottom, but it's going to have a 1/4 power, which is also known as a 4th root. And that would be the end of that particular story. And then we're off to our last page, which is problem number 12. So in problem number 12, we're going just a little bit further. Sorry, I'm off screen just for a second because I actually would like to make sure that I have my notes just so I don't make a silly mistake. But in this problem, we said we had $1,500 invested in an account that compounds at a rate of 6%. Now, notice it doesn't, there it is, it's monthly. So it's 1 plus 0.06 over 12. Raised to the 12t power. This is how much money I should have at any moment in time. And of course, it would make a lot of sense to find out, but 6% divided by 12 would just be 0.5% per month, 0.06 over 12. And so we have our 1,500, and I'm going to have 1.005 to the 12t power. And I would like to know, when am I going to increase my investment by 50%. So I used to have $1,500, but I want my $1,500 plus I also want an extra 50% of that. So I want an additional 750 in addition to the 1,500 I already had, right? So I'm looking for 2250. That's what I'm looking for. Now, the funny thing is when you do this, people immediately go, well, then let's divide both sides by 1,500. And what do you know? You get 1.5, which makes sense. I want my 100% of my money, but I would like an additional 50%. Thank you very much. So we're looking right here. And this is, again, one of those problems where we have something that doesn't have the nice base. So let's go ahead and take the log of both sides. This time I'm going to do a natural log because I can do whichever one I want. We're going to take the log of both sides. This is 12t times the log of 1.005. So t would be the natural log of 1.5. I need to divide both sides by 12 to make this go away. And I need to divide both sides by the natural log of 1.005 to make this portion here go away. So what that means is if I could take the natural log of 1.5 and divide it by parentheses 12 natural logs of 1.005, this should be the amount of time it takes. So I've got t equals 6.775 years. So if I could let my money run for just shy of 7 years, I should increase it by about that much. And that's actually a fairly modest rate of interest historically. If you put your money, say, in the stock market, is something like 6%. A lot of people hope to get more like 8, but I have not been that fortunate on my investments. And my last question talks about some radioactive material. And keep in mind, radioactive material is kind of a little bit of a different, and he wants to know what the half-life is. But he initially found that 50 micrograms of something, so that's my initial condition, decayed down to 40 grams. Interesting. So what I'm going to do is I'm going to use the A0E to the KT, or the formula PERT. It's just, we usually use it a little bit different in chemistry applications, but the amount that I have at some moment is my initial condition E to the KT. But in this particular case, it's set over a span of 6 years. Well, I just don't know what K is. I don't know what my percentage is. I know time, I know where we were, where we are, but I could divide both sides and I get 0.8. Now, one of the things that we mention always is take an intelligent log base of both sides. And so then what I have, if I took the log base E of both sides, we would do that because the natural log of E to the 6K would just be 6K. So all I need to do is divide both sides by 6. And so I took the natural log of 0.8, and I'm going to divide that by 6. And I got negative 0.037. The fact that it is negative is right because the thing is decaying. Remember, our rate would be positive if it's growing, negative if it's decreasing. So I now have my master formula, negative 0.037 T. And I would really, really like to know what my half-life is. So in other words, how long would it take to get down to that half spot? So if this is 50, we're going to call it 25. Now this should look familiar because if you divide both sides by 50, you get 0.5, just like before we got 1.5 on the previous problem. We're going to take an intelligent log base of both sides. And now all we need to do is I need to take the natural log of 0.5 and I need to divide it by the 0.37 number, which I have right here. So I'm going to divide that by the answer. And I got 18.638. Let's see, years. So I lost 80% in 6 years, but it would take me 18.6 years to get all the way down to 50%. Now, this is certainly not the only way to do this problem. There's actually quite a few ways to do this problem. In fact, a lot of people tell you to go ahead and use half-life values to do that, but I think that will suffice for now. And so I think that's where we should leave this, and I will see you again back in class. Have a good day. Thanks for joining me for a little bit. Bye-bye.